Hey, so I just had a thought. I wonder if you can tell me if f of x is always increasing. Is RAM an underestimate or an overestimate? What do you think? Yeah, I think when I draw an increasing function and I think about RAM here, RAM goes to the right side of the subinterval and comes back across. Right side, up and back across. So RM is going to be an overestimate for the actual value of the area under the curve. And we would say, if I needed to write, and I will need to write, hey, is this approximation, is this Riemann sum you've just done, is this an underestimate or overestimate? And you're going to say the estimate is an overestimate because f is increasing on that interval. Okay, nice. Now, in this video, I kind of want to look at some things where the subinterval widths are not the same from a table, but I kind of really want to start this process off by you doing a sort of reviewy problem. So here's your reviewy problem. Your reviewy problem is f of x equals 4 minus x squared on 0 to 2, and with estimate, or, just love the word choice options, approximate the area under the curve. And oh, by the way, under the curve really means between the curve and the x-axis. Okay, approximate the area under the curve from 0 to 2 using a right Riemann sum. Okay, so pause the video and give this one a try. Wait, I didn't tell you how many subintervals. Using 4 subintervals. Okay. Yeah, so take a few minutes, do this one, and come back. So I think I want to do this one from a table. I'm going from 0 to 2. We want 4 subintervals. So we're going to want this. And I know you're saying, but Mr. Kukla, that's 5 numbers. You wanted 4 subintervals. And so yes, I'm actually going to end up drawing the graph. 2, 4, 1, 1/2, 3/2. Look, 1, 2, 3, 4 requires 5 numbers, right? So what do we have for f of x? Well, if I plug a 0 in here, I get 4. If I plug a 1/2 in here, 1/2 times 1/2 is 1/4. 16/4 minus 1/4 is 15/4. If I plug a 1 in here, I get 3. If I plug a 3/2 in here, I get 9/4. 16/4 minus 9/4 is 7/4. And if I take a 2 and plug the 2 in there, I get 2 squared of 4. 4 minus 4 is 0. So I wanted to do a right Riemann sum. So I'm going to go to the right side of the subinterval and use those heights. In this case, I see my right Riemann sum, because this function is always decreasing, my right Riemann sum turns out to be an underestimate. And remember, Am I using this height? No, I would use this height if I were doing a left Riemann sum. Instead, I'm going to the right side of that subinterval and using the height there at 1/2. So I'm not going to use this value. I'm going to use all of these. So what will I have? Constant subinterval width, 15/4 plus 12/4 plus 7/4. So 27 34/4, 34/8, which I guess is 17/4. Okie doke, there's our right Riemann sum. Hey, you know, I think if you did a right Riemann sum, you could pretty quickly calculate the left Riemann sum. So will you find an approximation for the area under this curve using a left Riemann sum with 4 subintervals, please? We know Rn is 17/4. Okay, pause the video, write up the left Riemann sum. Hey, welcome back. So my subinterval width is still 1/2, but now I'm using the left side, so I'm using these values and not that one. So I've got 4 plus 15/4 plus 3 plus 7/4. Now, these numbers, by the way, when I added them last time, I got that. Well, now I'm just adding 4 halves, or 2, or 8/4 to that. And so LRAM, I would expect to be 25/4. Let's just confirm that. This is going to be 16/4 plus 15/4 plus 12/4 plus 7/4. 16, 31, 41, 43, 50/4. 50/4 reduces to 25/2, but still, look, I have to multiply by that 1/2. These cancel, and I get 25/4. Good. Now, is this table helpful for finding MRAM? Not if I'm doing 4 subintervals, because remember, with 4 subintervals, I need to go halfway across that interval to 1/4 and use that height. I need to go halfway across and use that height. So I think I need to just find those values. So I'm starting with 0. This is where a picture will help me. 2, 1, 1/2, 3/2. So if these are my intervals, I need here 1/4. And here, in between 1/2 and 1, 3/4. Between 1 and 3/2 is going to be 5/4. And between 3/2 and 2 is going to be 7/4. Very reminiscent of our pi/4 values. Okay, so I'm plugging this in here. 1/4 times 1/4 is 1. Oh, you should be doing this, shouldn't you? Did you already do this? If you haven't done this, get out of here. Pause that video and come back when you're done. So I've got 1/4 squared, which is 1/16. This is 64/16 minus 1/16 is going to be 63/16. All right, now 64/16 would be 4, and that's the value here. So our middle, if we go up to the middle, is just a little lower, If I plug a 3/4 in, that's going to be 9/16. 64/16 minus 9/16 is going to give me 55/16. If I plug in a 5 here, I'm going to have 25/16. And that's going to be 39/16. And finally, if I plug in a 7/4 here, it's going to be 49/16. 64 minus 49, I believe, is 15/16. Okay, and again, you know, at 2, the value of the function is 0, but over here at 7/4, we're saying that that value is near 1, not 1, just a little less than 1. So if I'm doing MRAM, I'm still using the subinterval width from 2 minus 0 over 4, subinterval width is 1/2. Okay? This is not the subinterval width. We're going from 0 to 1/2. 0 to 1/2 is this 1/2 subinterval width. We go to the middle of that interval, go up to the function to find this y value. So my MRAM in this situation would be 1/2 times 63/16 plus 55/16 plus 39/16 plus 15/16. 110, 120, 130, 140, 150, 164, 169, 172. I get 172 over 32. And feeling a little lazy, like, yeah, I know 4 goes into both of those, but okay, so that's 43. 4 times 4, 3, 112. 4 goes in, yeah, over 2. No, 4 goes in, so that's going to be over 8. Yeah, so either any of these. In fact, on the AP exam, when it shows up on free response, you can leave it here, and I recommend it. Yeah. Okay, so that's a little review. Let's take a quick look at what to do if I have a table. All right. So let's say, remember yesterday we started with times and velocities, and I want to approximate the distance traveled in the first 7 years. And so my table says 0, 1, 2, 5, 7. And this is 8, 10, 11, 15, 18. Well, tell me, are my subinterval widths the same? Here, the distance is 1. Here, the distance is 1. Here, the distance is 3. Here, the distance is 2. The subinterval widths are not the same. So what I'm going to do is find the area of each rectangle, but I'm not going to be able to pull out that constant subinterval width. I'm also not going to do 7 minus 0 over 4. That's not going to work for me either, because that's going to say 7/4, and while I do start at 0, I don't have a value at 7/4. I don't have a value at 14/4. So I can't use the methods we've done. Some students find it helpful, and I don't know if you will, but some students find it hard to do this problem from a table. For example, if I'm looking at LRAM, remember, LRAM uses the first but not the last. So if I'm thinking about LRAM, I'm thinking about this rectangle. Subinterval width is 1 times, in fact, some people write this as 1 minus 0 times, which height do we do? Well, I'm doing LRAM, so I'm using the height on the left side of the interval, plus the next subinterval, 2 minus 1, and here's the next subinterval, and again, I'm using this left value, plus, now we have this subinterval, 5 minus 2, times again the left side of that subinterval, plus our last rectangle goes from here to here, and we use the left side value. So that's going to be 7 minus 5 times 15. This is actually sufficient to earn the point on the AP exam. Many students find a need to go further, and occasionally College Board actually wants you to recognize what this number is and then compare it to something else. And if I have to compare this number to something else, I really don't have a sense of what number I'm looking at here. So I'm going to, in fact, tidy this up to be 8 plus 10, because 2 minus 1 is 1. 3 times 11 is 33, and 2 times 15 is 30. So 63, 73, 81. So my approximation of the, oh, and I guess we need a velocity here. So how about feet per year? And so I can say, when I multiply the time times the feet in years times feet per year. What I'm getting here is feet. Those are feet. Yes. What's the change in position? What's the displacement? Approximately 81 feet over the 7-year interval. Okay? So, how about you do an approximation for this one? Earth. Okay. T and well, I actually wanted to say one more thing about that last one, so I'm going to go back and say that thing. Some people find it helpful to graph it. 5 and 7. So 0, 8, 1, 10. Ooh, I better make 8 much lower than that. There's 8. 1, 10. 2, 11. 5, 15. And 7, 18. And the reason I said graph this is because now you can actually see, okay, left, go up to the curve, and then come across. Go to the left side of the interval, up to the curve, and come across. Go to the left side of the interval, come up to the curve, and go across. Go to the left side of the interval, up to the curve, and go across. And so I can see each time, especially if I sort of sketch in here, for this increasing function, my LRAM is in fact an underestimate. I'm not counting these bits. And maybe it's easier for me to say now, okay, LRAM is going to be 1 minus 0, this distance, times that height on the left side, plus 2 minus 1, times, I need the height on the left side, plus 5 minus 2, times, I need the height on the left side, plus 7 minus 5, times, I need the height not over here, but the height on the left side, 15. So I can get that same setup, not just from a table, but from sketching the graph from the table and then visualizing the rectangles. This is going to take more time because you have to draw the picture, but if you're finding yourself challenged by doing this problem just from a table, then that might be something to do. So let's take a look at this one. We've got 0, 5, 10, 13, 15. And I'm looking at velocities, let's say miles per second. And these are seconds. 20, 22, 28, 30, 18. Okay, so again, what I want to know is if I've got this seconds and miles per second, and I've got these values here, 0, 20, and no, I don't want to do it that way. I don't want to use the graph. You can use the graph. I want to use the table. I want you to find LRAM. I want you to find RRAM. And sometimes College Board uses some language like, use the number of subintervals that are suggested by the data. 1, 2, 3, 4 subintervals are suggested by the data. But they don't tell you with n equals 4. You have to figure out that there would be 4 subintervals here. Okay? So yeah, will you please go and calculate your approximations for area under this velocity curve. Find the area under this, it's miles. Under this velocity curve, no, approximate, estimate the area under the velocity curve. Using LRAM, using RRAM, a left Riemann sum, a right Riemann sum. Pause the video, come back, and we'll take a look at those. Hey, welcome back. so it looks like I have a constant. Oh, no, I don't have a constant subinterval width. So I'm going to write this LRAM up as 5 minus 0 times 20 plus 10 minus 5 times 22 plus 13 minus 10 times 28 plus 15 minus 13 times 30. And that's going to be my LRAM. Remember, LRAM uses the first height and not the last height. RRAM doesn't use the first height, does use the last height. So RRAM is going to be those heights. Now my first subinterval is still 0 to 5. 5 minus 0, but I'm using that height. 22 plus 10 minus 5, same, but not 22, but instead 28, plus 13 minus 10 times 30, and finally 15 minus 13 times 18. Okay, so those are my values for LRAM and RRAM. And you know, we could even do an MRAM here. Now, the problem with doing an MRAM here is, no, I don't have enough information to do an MRAM with 4 subintervals. No, I can't really do an MRAM. Sorry, I take that back. This is what I would say instead of doing an MRAM. Sometimes College Board gives you the information like 0, 4, 8, 12, 16, and they say, hey, why don't you do an MRAM here with the intervals suggested by the data. Okay, so we're going to have 5, 12, 2, 15, and 0. So if I'm doing MRAM, I need the middle of the subinterval. Well, I don't know a number between 0 and 2. So I guess my subinterval width can't be 4 because I don't know something in between. But if my subinterval width was 8, then I would have halfway across that interval what the height is. If my subinterval was 8, then I do have halfway across the subinterval the height. So yes, I could make MRAM work here, but not with n equals 4, only with n equals 2. How would I set that up? Well, remember our subinterval width here is 8 times the height halfway across, plus the second rectangle, 16 minus 8, times what's the height halfway across? 15. And so there could be my MRAM approximation. Good, excellent. I think this is fabulous. Are we ready? I think we're ready. I'd like to take a look in the next video at trapezoid sum. Yeah, let's take a look at trapezoid sum. Should we do that now? Oh, how scandalous. Yes, let's actually put these together because that last video, or the first part of this video, is actually for an assignment that doesn't exist called 79A. So let's combine 79A and 80. I really felt like the first video, it was an hour, you were already sort of tuckered out. You definitely didn't need me to be talking about tables, okay? So yeah, I had to get that in. But now let's focus on trapezoid sum. Trapezoid sum. So here's the thinking. The thinking is that if I have this curve and I have these subintervals and I'm making these rectangles, here's the thing about these rectangles. It's either undercounting or it's overcounting. So what could I do about that? Well, we had talked about averaging this underestimate with this overestimate, right? That would be our LRAM value This would be our RAM value. And so we want to talk about maybe averaging those two. And so we had said RAM plus LRAM divided by 2 is a better approximation than either RAM or LRAM alone. It's just a lot more work, and so generally I'm not particularly keen to do it. But let's consider this. What if we have our little LRAM line, we have our RAM line. What if we do this? Now, this is a curve, and this is a straight line. I've got a curve, and I got a straight line. This is the stuff I'm not counting, instead of all of this and all of this. So, yeah, if I can average these values, I get really close to the actual value. Still an approximation. You know, I'd have to let n become a really big number in order for these to get much, much closer. But, yeah, so, yeah, I really am just looking at this saying, okay, drawing in the diagonal. My curve is doing something like that. But when I draw in that diagonal, that's splitting this area in half. That overcount, that undercount, and then if we add those together and divide by 2, it looks like that. And furthermore, look what happens. What shape is this that we've got now? Yes, that's right, it's a trapezoid. So let's take a look at trapezoids. First, if you haven't remembered the formula for area of a trapezoid, 1/2 height base 1 plus base 2. And when we look at these trapezoids, our trapezoids will often look like this. Here's my B1, here's my B2, here's my height. I know, you want this to be height. I'm sorry, the height is here. The height is going to be our subinterval width. The bases are always going to be the y values of the function. Okay, and so I'm going to use that area formula, because what I'm getting then is this area, and oh, I'm just missing a little tiny bit. Okay, so this is the formula we'll be using, and I kind of want to take a moment to consider a situation. So I've got this situation here, and I've got these subintervals. I'm using a consistent subinterval width, so I'm going to call this delta x, 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 and I've grown weary, so I'm going to throw that one away. You can't do that. This is going to be y sub o, y sub 1, y sub 2, y sub 3, right? This height, this y value, y sub 4, y sub 5, y sub 6, and y sub 7. Okay. So I want to figure out what the trapezoid sum would be here. Okay, so trapezoid sum is going to be 1/2. And remember, my trapezoid has a height, delta x, and then base 1 plus base 2, y sub o plus y sub 1. And then the area of the next one is going to be 1/2 delta x, y1 plus y2. And then 1/2 delta x, y sub 2 plus y sub 3, plus 1/2 delta x. I know you're saying, Mr. Kugler, do we really have to do 7? Okay, we won't do 7. How about we'll stop here? Okay. So I've got y3, and here will be y3 plus y4. Now, I definitely see that I can pull out all these 1/2s and all these consistent subinterval widths. And if I do that, I get y sub o, y sub 1 plus y sub 1 plus y sub 2 plus y sub 2 plus y sub 3 plus y sub 3 plus y sub 4. Okay? And now look, same z's, same z's, same z's. So really what I could do here is say 1/2 delta x y sub o plus 2 y sub 1 plus 2 y sub 2 plus 2 y sub 3 plus a y sub 4. Okay? That's my shortcut formula. Like, no, I don't want to derive it. And no, I don't particularly want to write the equation of, like, there's the area of that first trapezoid. I don't want to have to do all that writing if, in fact, this process, finding the area of all these trapezoids, actually can be distilled down to this. Remember, this is our sub-interval width. And what are these? These are the heights. These are the y values at each of those points. And notice, I use 1 of each end and 2 of all the middle ones. So if I have a table, 0, 1, 2, 3, 4, and I'm looking at some values here. I don't know, so these are seconds, and these are feet per second, and I've got 4, 8, 2, 0, 6. Well, the subinterval width is the same. I have a subinterval width of 1, so 1/2 times 1. 1 of the first heights plus 2 of all these middle heights, and only 1 of this last one. And that's it. That's all I have to do. So trapezoid can be this really long and involved thing, especially when I don't have a consistent subinterval width. That's the only time I really need to do this, when my subinterval width isn't the same. If subinterval width is the same, if we have a constant subinterval width, use this formula. It saves a lot of time. 1 of the first and last heights times 2 of all the middle ones times, don't forget this is a trapezoid, 1/2 base times height. I'm sorry, 1/2 height. And this represents all my B1 plus B2s that I'm looking at down here. All right, so shortcut, but the shortcut only works when we have a consistent subinterval width. And I want to say something about this trapezoid formula. You know, we have this understanding of trapezoid formula, or I'm thinking about distributing this delta x and this 1/2 to each of these. But I kind of want to go back and just sort of make a comment. Let's see if that comment can fit here. If I were doing LRAM, here, my area would be this times this. Okay, so I'd have delta x, y sub o. And if I wanted to do LRAM here, I would do subinterval width times this height, y sub 1. So delta x, y sub 1. And then I would continue over here. I'd have delta x, and now I'd have y sub 2. Delta x, y sub 2. And then finally, because we're not going past y sub 4, finally I'd have delta x times y sub 3. So that's my LRAM. And what would my RRAM look like? My RRAM, and I wish I had just a little bit more space. My RRAM is going to be the area of this rectangle. So it's actually using this height, y sub 1. So I'm going to have delta x, y sub 1, plus delta x, y sub 2, plus delta x, y sub 3. That's this one, right? But now I got to go out to that one as well. So plus delta x, y sub 4. Now notice what we have here. We have one of these, and one of these, and we have two of each of the middle ones. Wait a minute, Mr. Google. I thought you were talking about LRAM and RRAM. And I am. But if I take LRAM and add it to RRAM and average them, right? I'm going to have that underestimate. I'm going to have that overestimate. I'm going to have that underestimate, and I'm going to average them. If I add LRAM and RRAM, add them together, divide by 2. Divide by 2. Divide by 2. Subinterval width. Look, I see the subinterval width everywhere here. I can pull out that subinterval width. And so this representation here is actually me adding up all those y values. I have one of the first one, I have one of the last one, and I have two of each of them in between. So the shortcut formula is LRAM plus RRAM divided by 2. I will say, though, that the students who do not use the trapezoid rule, the shortcut here, but instead say, I'm going to find LRAM and RRAM and divide by 2, they run out of time on tests, because this is so much more labor intensive to find LRAM, to find RRAM, then add those two numbers and divide by 2. When I have a consistent subinterval width, I can use this shortcut and should, and if I don't have a consistent subinterval width, then I've got to use this, where I find the area of each of those trapezoids and add those areas together. And that's what you should be prepared for. Whether we're talking about some sort of algebraic function, like, I don't know, how about y equals 4 minus x squared? Let's want to approximate the area on 0 to 2 using n equals 4. Find a trapezoid approximation. Okay? I don't want to do this first one. You do the I'll do the first one, but you've got to do the next one. So 2 minus 0 over 4 gives me 1/2. My subinterval width is 1/2. And if I'm thinking about a table of values here, do you like the horizontal table or do you like the vertical table? Time. I don't have time. I have x's and y's. 0, 1/2, 1, 3/2, 2. I plug a 0 in here, I get 4, 1/2. It's going to be 1/4, 16/4, that's 15/4. I plug in a 1, I get 3. I plug in a 3/2, that's 9/4. 16 minus 9 is 7/4. I plug in a 2, 2 squared is 4, 4 minus 4 is 0. So what's my trapezoid approximation going to be? Well, the subinterval width is the same everywhere. The subinterval width is 1/2. And because the subinterval width is 1/2, I can, as in a constant, I can use my shortcut. So, what's wrong with what I'm writing? 1 of the first type, 2 of the second, 2 of the third, 15/4, 2 of the third, 2 of the fourth, plus 1 of the last one. What's wrong with this? Remember, our trapezoid area formula is 1/2 delta x y sub o plus 2y sub 1 plus 2y sub 2 plus, and so on, to y sub n minus 1 and only 1 y sub n. So, don't I have that? 1 of the first, 1 of the last, and 2 of each of the ones in between. And I have a 1/2. Oh, but wait. Delta x was that 1/2. We said our subinterval width was 1/2. So the reason this is wrong, and this is actually really a common student mistake, they find the subinterval width and they multiply the subinterval width the way they're supposed to. But they forget that, in fact, the area of the trapezoid, like the area of a triangle, comes with a 1/2 in it. And so I really need that out there as well. Okay, so I'm going to have 1/4 times stuff. Now, if this is on free response, you stop here. Just stop. Because there's so many possibilities of you doing common denominator, adding error, multiplying by 1/4. Yeah, it's just fraught. But free response, I can stop here. Multiple choice, I'm going to have to take it further. But free response, we stop there and smile. Okay. Any questions about this? Now, should we do one where we don't have a consistent subinterval width? Or do you want to do where we find LRAM and RRAM and add them together and divide by 2 to get that value? You know, I don't want to do that either. I do want to do it. Yeah, I want you to do one. That was it. So we should either be able to do any of our approximation methods, LRAM, RRAM, MRAM, or now trapezoid sum, given a function. You know, they give me a function like we saw 4 minus x squared. I should be able to do an approximation based on that. I should also, for L and RRAM, you know, if I see that the function is decreasing, or if I see that the function is increasing, I need to be able to comment on whether or not LRAM is an overestimate or if LRAM is an underestimate in those situations. They love asking that question. That's going to be a guaranteed ask. So please make sure you got that from the last video. How about you do this one? Let's have seconds and feet per second. 0, 3, 4, 8, 10. We've got 5, 2, 7, 4, 3. And I'd like you to approximate the displacement or change in position on 0 to 10 seconds. Okay? Trapezoid sum, not LRAM, not RRAM, certainly not MRAM. Trapezoid sum. Go to it. Pause the video, give it a go, and let's see how things come out. Okay, welcome back. So remember formula for area of a trapezoid. And since we're talking about y values, I probably want, we're talking about velocities, v sub 1 plus v sub 2. That's our area of, well, I guess these are times. There we go. So what am I going to have? My first rectangle is going to have a subinterval width of 3. 1/2, 3 minus 0, base 1 plus base 2. And then here, 1/2, subinterval width, 4 minus 3, base 1 plus base 2. Plus this one, 1/2, 8 minus 4, 7 plus 4. So this 4 is here, and this 4 is here. Plus our last trapezoid here, which is going to be 1/2, 10 minus 8 times 4 plus 3. And of course, you're more than welcome to simplify this as you go. So in that case, I would have 1/2, 3 times 7, right? 3 times 7 plus 1/2. Ooh, the distance here is 1 times 9 plus 1/2. The distance here is 4. The sum of those heights is 11 plus 1/2. The subinterval width is 2, and the sum of these is 7. So for the purposes of sanity, I've got 21 plus 9 plus 44 plus, so that was 2 times 3, 6. So 50 60, 80 divided by 2 is 40 feet. My approximation is 40 feet. The approximate displacement, the change in position on 0 to 10, 40 feet. Notice I'm not using the position function. I'm not doing s of 10 minus s of 0. That's what we're computing here. We're saying that the position at 10 minus the position at 0, the change in position is about 40 feet. But this isn't position. This is velocity. We're using velocity to say something about position. And I don't know if you remember, but I'm using the derivative of position to say something about the antiderivative of velocity. The antiderivative of velocity is position, and I can say something about the antiderivative simply by using that original function. And we're going to be doing a lot more of that. But I think it's time for us to be done with approximations. I mean, we can approximate, and sometimes we're put in the position where we can't actually find the actual value, and we have to approximate. But most of the time, thanks to the work of a whole bunch of people, we are actually able to figure out what the actual area under that curvy thing is. And that's what I want to head to next. Yeah, that's what I want to head to in the upcoming videos. See you.